The story of I. Complex numbers were not invented to satisfy abstract curiosity. They were forced into existence by a very concrete problem: solving cubic equations of the form x cubed plus px plus q equals 0. By the early 1500s, Italian mathematicians had found a general formula for solving cubics. It worked, except in one specific situation. Whenever a cubic had 3 distinct real roots, the formula demanded that you take the square root of a negative number as an intermediate step, even though the final answer was a perfectly ordinary real number. This case earned its own name: casus irreducibilis, the irreducible case. Let's understand this with an example. Take the equation x cubed equals 15x plus 4. By inspection, x equals 4 is a solution. 4 cubed is 64, and 15 times 4 plus 4 is also 64. That is a fact you can check with nothing but ordinary arithmetic. No imaginary numbers required anywhere. Now apply the general cubic formula, the one tool meant to work on any cubic, not just ones you happen to be able to guess. And it hands you this instead: x equals the cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of negative 121. There is no way to reach 4 through this formula without manipulating the square root of negative 121 along the way. A 16th century mathematician had exactly 2 options: declare the formula broken whenever this happens and fall back on guesswork case by case, or treat the square root of negative 1 as a legitimate object you're allowed to compute with and see what happens. Raphael Bombelli chose the second path in 1572. He set the square root of negative 121 equal to 11i, guessed that the cube root of 2 plus 11i might equal 2 plus I, and simply checked it by cubing. 2 plus I cubed equals 8 plus 12i plus 6i squared plus I cubed, which equals 8 plus 12i minus 6 minus I, which equals 2 plus 11i. It worked. By the same logic, the cube root of 2 minus 11i equals 2 minus I. Add the two cube roots together: 2 plus I plus 2 minus I. The i's cancel completely, and you land exactly on the real answer you already knew was correct. That cancellation is the whole argument. Mathematicians did not start trusting the square root of negative 1 because someone found it philosophically appealing. They trusted it because a method that treated it as a legitimate, computable object kept producing correct, independently verifiable real answers. Answers the safe, real numbers only approach could not reach at all. No single person invented complex numbers. Each stage below added something the previous one was missing. Bombelli, in 1572, worked out the arithmetic, showed the detour cancels. Descartes coined imaginary as a dismissal. Euler, in 1748, introduced I and connected it to e to the I theta equals cosine theta plus I sine theta. Wessel, in 1799, and Argand, in 1806, independently gave it a geometric home. And Hamilton later formalized the complex numbers as ordered pairs, removing the mysticism. There are 2 equally important lenses here: algebra and geometry, and a viewer needs both, not just one. The real number line is algebraically incomplete. Plenty of simple polynomials, x squared plus 1, for instance, have no root on the real number line at all. Adjoin I, the square root of negative 1, and close the system under addition and multiplication, and you get the complex numbers all a plus bi, with a and b real. The payoff is the fundamental theorem of algebra. Every polynomial of degree n with complex coefficients has exactly n roots in the complex numbers. No exceptions, no special cases. Let's graph this curve. Y equals x squared plus 1. Its lowest point sits at 0, 1. The curve never comes down far enough to touch the x-axis. Looking at that picture, you'd reasonably say no roots done. And on the real number line, you'd be right. No real roots exist. So what does it mean that the equation has roots I and negative I? The key move: those roots simply don't live on the graph you just drew. That graph only shows what happens for real inputs. The moment you allow a complex input, you're asking a question the 2D picture was never built to answer. Check it directly. Plug x equals I into x squared plus 1. I squared plus 1 equals negative 1 plus 1 equals 0. Try to point to x equals I on the real axis, and you can't. It isn't there. Here's a way to see it happen, not just accept it. Watch this family of parabolas. Y equals x squared minus 4x plus c as c increases. While c is below 4, the parabola dips below the x-axis. Two real roots, clearly visible, sitting right there on the real axis. At c equals 4, the parabola is exactly tangent to the x-axis, one doubled real root. Past c equals 4, the parabola lifts clear of the x-axis, no visible real roots. At this exact moment, the two roots peel off the real axis and move symmetrically up and down into the complex plane, and the vertical distance between them keeps growing as c increases. Watch the two panels together. How far the parabola floats above 0 on the left is exactly how far the roots have moved off the real axis on the right. Here's a way to make that meaning concrete rather than mystical. Every quadratic with imaginary roots can be rewritten as x minus a squared plus b squared, with roots of plus bi and a minus bi. X squared plus 1. Here equals 0, b equals 1, and the parabola's minimum sits at 0, 1. X squared minus 4x plus 13 equals x minus 2 squared plus 9. Roots are 2 plus 3i and 2 minus 3i. The minimum sits at 2, 9, well above the axis. So the real part of a root, a, tells you where the parabola's minimum sits horizontally, and the imaginary part, b, tells you how far above the axis it's floating, literally, how badly it misses 0. An imaginary root isn't nonsense. It's compressed information about a real, visible curve. This parabola almost touches 0 around x equals a, but floats b squared units too high to actually make it. The real number line is one-dimensional. Every real number is a single point on a line, and any two real numbers can always be compared. 3 is less than 5. Complex numbers don't fit on this line at all. They need a second dimension entirely. A complex number of plus b, I is the point a, b in a plane along the horizontal, real axis, and b along the vertical, imaginary axis. This is the Argand plane. In this plane, addition of complex numbers behaves exactly like ordinary vector addition. Multiplication is where things get interesting. It does something addition can't. When you write z equals a plus b, I in polar form, its magnitude is given by the length of z equals the square root of a squared plus b squared. It is a real number telling you how far, and angle theta tells you in what direction. Whenever you see I, think rotation. Take the point 1, sitting at 1, 0 on the real axis. Multiply by I. Land on I, the point 0, and a quarter turn counterclockwise. Multiply by I again. I times I squared is negative 1. The point negative 1, 0, half a turn total. Again, negative 1 times I is negative I. Point 0, negative 1, 3/4 turn. Again, negative I times I is 1. Back to the start, a full circle. for multiplications by I, for 90-degree steps back to where you began. That's not a coincidence to just accept. It's forced entirely by the single rule I squared equals -1. More generally, write any complex number in polar form. Z equals or times cosine theta plus I sine theta. Multiply two of these using the ordinary trig sum identities. Magnitudes multiply, angles add. Multiplication was quietly always rotation. The algebra just needed to be written in polar form to reveal it. Worth walking through slowly because it upends the intuitive order of discovery. The geometry did not come first. It was attached afterward, as an interpretation of algebra that already existed and already worked. Abraham de Moivre was working on a different problem, taking roots inside Cardano's cubic formula, the same casus irreducibilis problem. He found and proved geometrically the pattern cosine theta plus I sine theta raised to the n equals cosine of n theta plus I sine of n theta. At this stage, it's purely a trigonometric identity dressed up with I. There's no sense yet that I represents a plane or rotation as a concept. This is the real breakthrough, and it happened through pure algebra, comparing infinite series that, on the surface, look completely unrelated. A quick word on where these series actually come from, so you're not just taking them on faith. A Taylor series builds a function from its own derivatives at a single point. For e to the x, every derivative is e to the x itself, and e to the 0 is 1. So every coefficient collapses to 1 over n factorial. For cosine and sine, the derivatives cycle every 4 steps. Cosine, negative sine, negative cosine, sine, and back to cosine. Evaluated at 0, that cycle is 1, 0, -1, 0, repeating exactly why cosine series keeps only even powers with alternating sign. Sine cycle, offset by 1 step, is 0, 1, 0, -1. Exactly why sine series keeps only odd powers with alternating sign. Substitute x equals I theta into the exponential series and simplify powers of I. I squared is -1. I cubed is -I. I to the 4th is 1. I to the 5th is I, repeating every 4 terms. E to the I theta equals 1, plus I theta, minus theta squared over 2 factorial, minus I theta cubed over 3 factorial, plus theta to the 4th over 4 factorial, plus I theta to the 5th over 5 factorial, minus, and so on. Group the terms with no I separately from the terms carrying an I. No I terms, exactly the cosine theta series. I terms, exactly the sine theta series multiplied by I. Therefore, e to the I theta equals cosine theta plus I sine theta. Euler, 1748, Introductio in Analysin Infinitorum. De Moivre's older identity now falls out as an easy corollary. Cosine theta plus I sine theta to the n equals e to the I theta to the n equals e to the I n theta equals cosine n theta plus I sine n theta. One line, once you have the exponential form. Plug in theta equals pi radians, 180 degrees. E to the I pi equals cosine pi plus I sine pi equals -1 plus I times 0 equals -1. Rearranged, it gives Euler's identity. E to the I pi plus 1 equals 0. What's genuinely striking here? Euler didn't set out looking for the geometry of I. He was manipulating power series, pure formal algebra, and the rotation meaning fell out afterward, as an interpretation of a result he had already derived. The geometry was discovered after the formula, not before it. Only after Euler's algebraic result existed did anyone ask, what does this actually mean as a picture? Caspar Wessel, a Norwegian-Danish surveyor, in 1799, and Jean-Robert Argand, in 1806, independently proposed plotting a plus b I as the point A, B in a plane. Once you do that, e to the I theta equals cosine theta plus I sine theta is instantly recognizable as the point on a unit circle at angle theta. That's the moment multiplication as rotation became a visible, intuitive fact rather than a symbolic curiosity. This is the payoff, a direct consequence of Euler's formula, plus one observation from calculus. Where does this equation actually come from? A mass on a spring feels a restoring force proportional to displacement. Hooke's law, F equals negative kx. Newton's second law says force equals mass times acceleration, m times the second derivative of x. Put them together, m times the second derivative of x equals negative kx, or, dividing by m, the second derivative of x equals negative k over m, x. Define omega squared as k over m, and this becomes the equation for simple harmonic motion. A mass on a spring, no friction, d squared x dt squared equals negative omega squared x. Verify by direct substitution that x of t equals e to the I omega t solves this. The second derivative of e to the I omega t is I omega squared times e to the I omega t, which is negative omega squared, times e to the I omega t. It works algebraically, instantly, using ordinary exponential calculus rules, far less painful than juggling sine and cosine derivatives by hand. Here's what that solution actually looks like. E to the I omega t traces a helix, spiraling upward through time. Its shadow on one wall traces cosine omega t, the real part. Its shadow on the other wall traces sine omega t, the imaginary part. Both are happening at once, forever, out of a single rotating number. But e to the I omega t is complex. Where's the actual, physical, real position of the mass? Apply Euler's formula. E to the I omega t equals cosine omega t plus I sine omega t. The physically real position is just the real part x of t equals cosine omega t. A plain, ordinary back-and-forth oscillation, exactly what you'd see on a real spring. The imaginary part, sine omega t, isn't wasted. It tracks the velocity phase 90 degrees out of step with position, which is physically correct. Velocity peaks exactly when position crosses zero. A single complex number, rotating steadily around the unit circle, is secretly carrying both position and velocity at once. The physical position is just the shadow it casts on the real axis as it spins. The general pattern, whenever a system's governing equation looks like rate of change, equals I times something times current state, the solution is automatically a steady rotation in the complex plane, and the real, measurable physical quantity is just the real axis shadow of that rotation. That's the entire mechanical reason wave equations are full of I's, not decoration, but the most economical way calculus has to encode goes around in circles forever, neither growing nor shrinking. Honest answer, and it's a little unsatisfying at first. I is never a quantity you directly measure. No voltmeter reads 3 I volts. No ruler measures 2 I meters. So if it's not a measurable thing, what work is it actually doing when it shows up in physics equations? Answer: I is bookkeeping for two real things that are permanently linked and rotate into each other. A swinging voltage, 5 cosine of omega t plus 30 degrees, needs two real numbers to describe it fully. How big it swings, 5, and where it sits in its cycle at time 0, a 30-degree offset. Rather than carry both numbers separately through pages of trig identities, engineers write it as the real part of 5e to the I 30 degrees times e to the I omega t. The complex number 5e to the I 30 degrees is just 5 and 30 degrees zipped into one object you can add and multiply algebraically. At the very end, you always strip I back out and report a real, measurable voltage. Here, I is scaffolding. Useful, but disposable once you're done. Consider the simplest possible differential equation. dy dt equals ky. If k is real, y of t equals e to the kt. Pure growth when k is positive, or pure decay when k is negative. Runaway or die out. No oscillation. If k is imaginary, say k equals I omega. Y of t equals e to the I omega t equals cosine omega t plus I sine omega t. This never grows and never decays. It just rotates around the unit circle forever, same size for all time. Anything in nature that oscillates without losing or gaining energy, an idealized frictionless pendulum, a light wave in vacuum, an electron in a stable atomic orbital, has to be described by a differential equation whose rate constant is imaginary, precisely because that's the only way to get sustained rotation instead of growth or decay out of an exponential. I, as the mathematical fingerprint of this system, trades something back and forth forever, without net loss. One question arises: are complex numbers mathematically necessary, or merely convenient notation? No, you're never strictly forced to write I anywhere. Everything complex numbers do can be reproduced with real numbers alone, if you're willing to carry extra bookkeeping. Take the voltage phasor, split into magnitude and phase, two real numbers instead of one complex one. Take the rotating helix, split it into its cosine track and its sine track, running side by side. There's no mathematical result and no known physical system where complex numbers are logically required. Everything reduces to real numbers if you're willing to pay in extra variables, extra bookkeeping. What complex numbers by you isn't new reachable territory. It's compression, replacing two coupled real quantities and their rotation rule with one symbol in ordinary algebra. Using I is not necessary, but irreplaceably efficient. Thanks for watching The Wandering Analyst. If this was worth your time, consider subscribing for more.